Hi, today we're here to learn how to work multi-segment one-dimensional word problems. So the motion is going in one direction, but there are going to be different segments where different things are going on in each segment. And we're going to have to incorporate parts of the problem that went before us to the part of the problem that we're working on now. So let's take a look at our problem. This is, and for your reference, this is going to be Kinematics Packet 7, problem number 6. And the problem reads, a rocket rises vertically. So this is delta y's, meaning height, from rest. So that's going to be initially our VI is going to equal 0 meters per second. That's something you have to assume, with an acceleration of 3.2 meters per second squared until it runs out of fuel at an altitude of 950 meters. After this point, the rocket is in free fall, which means acceleration switches from 3.2 meters per second to negative 9.8 meters per second squared. So we're going to answer the following segments of this problem. The following parts. What is the velocity of the rocket when it runs out of fuel? How much time does it take to reach the point at which it runs out of fuel? What maximum altitude or height does the rocket reach? How much time total does it take for it to reach the maximum altitude? With what velocity does it strike Earth? And how much time total is it in the air? So all physics problems do start with a picture. So here's my picture, but you have to pay attention to details. So at the first part, the rocket is going up and it's getting faster and faster and faster at 3.2 meters per second squared. It's speeding up, and you can see down here that the rocket is firing hot gas out of it as it burns fuel. The rocket runs out of fuel. There's no hot gas here being slammed out of the rocket. And that means there's no more acceleration upwards. So the rocket still goes upwards, but it's now having another force acting upon it. Well, that force was already there. It's gravity, but there's nothing to really overcome that force. So the rocket's going to go up slower and slower and slower, as if you were tossing a ball up, because there's no force that you're applying to that ball anymore once it leaves your hand. And then the rocket, it's going upwards, but it's slowing down. So we'll call that negative acceleration. At the highest point, the rocket is stopped. It is stopped ever so briefly until it can go until it starts its descent downward. And when it goes downward, it's going to be accelerating negatively again, but the acceleration due to gravity is negative 9.8 meters per second squared. It gets faster and faster in the negative direction. So we've got two segments where there is negative acceleration for different reasons, and one segment, the first segment, where it's going has positive acceleration. So in this table, we have to assume some things and we have to realize that some things are given to us. So what's really important here is that not always is your VI going to be the same thing or your VF. Your VF the VF in segment 1 becomes the VI, or your initial velocity, in segment 2. And we'll go over that as we go through the slides. And in this problem, we're not going to be learning any new equations. We're going to be using what we already have. So equations 1 through 4, kinematics, one-dimensional motion, and we're going to be using the y form of the equations because delta y is going to be for the change in height. So take a look at these. They should be familiar to you. Mostly we're going to be using equations 2 and 4. 1 has no place here because there is no constant acceleration, and number 1 has no place here because there's no constant velocity. There's always going to be acceleration in this problem. Okay, so let's look at segment 1. The rocket is accelerating upwards at 3.2 meters per second squared to a height of 950 meters. So in segment 1, it asks you, what is the velocity of the rocket when it runs out of fuel? So we are given in the problem delta y, or the height, is 950 meters. We are given that acceleration equals 3.2 meters per second squared, and we have to assume that our VI, our initial velocity, is going to be 0 meters per second because it is on the launch pad and it starts at rest. So we then have to select an equation. I chose to go with VF, or velocity final squared, equals velocity initial squared plus 2a times the delta y, or the height. VI, or velocity initial, goes to 0, so it drops out of the equation. So we end up with VF, or final velocity squared, equals 2a change in y, or height. So VF is going to equal the SQRT of 2A delta y. We plug our numbers in and we choose the positive form of when we take the square root, which would be positive 77.97 because the rocket's going in the upward direction at this time. So that would be VF, final velocity equals 77.97 meters per second. So to do to figure out part B, where it says how much time does it take the rocket to reach the point in which it runs out of fuel, I'm going to then use a slightly different equation. VF, or final velocity, equals VI, initial velocity, plus A delta t, or acceleration times the change in time. Again, VI is 0 here, so it drops out of the equation. So I then rearrange my equation to be delta t equals the final velocity divided by acceleration. I plug in my numbers, and my meters per second divided by meters per second squared, and I work out my units, and I end up with seconds, so I know I set up my problem correctly. And my delta t is going to equal 24.37 seconds. So the rocket's is going up, faster and faster with a max speed for this segment of the problem at the end when it runs out of fuel of 77.97 seconds, and it took 77.97 meters per second, and it took 24.37 seconds to get there. Segment 2, the rocket can no longer accelerate upwards. That is because it's run out of fuel, and an object in motion will stay in motion. However, gravity is really acting on this rocket now, and it's going to be slowing it down because there's no longer fuel to counteract that. So the rocket is still going upwards, but the acceleration is getting lesser and lesser and lesser, so the rocket is now in negative acceleration mode. So what is the maximum altitude that this rocket can reach? Well, we know that the acceleration is now changed. It's no longer 3.2 meters per second squared. It is negative 9.8 meters per second squared. My yi, or my initial height, notice the initial now starts at 950 meters. My vi, my initial velocity, was my final velocity in the previous part of the problem, and that is 77.97 meters per second. My final velocity, that is at the end of this segment, and that is going to be 0 meters per second. That is because that rocket is going to have to change positions, and it's going to have to go downwards. It cannot be going upwards and downwards without stopping, so that VF is going to be 0 meters per second. You have to assume that information and apply it here. My Y final, I don't know what it is yet. I don't know how far this rocket goes. And my delta y for this segment, I do not know what it is yet. So I'm going to choose an equation, and for the equation, for the information I have, I'm going to go with final velocity squared equals initial velocity squared plus 2a delta y. And the final velocity goes to 0 in this part of the problem, so I can eliminate it. My delta y is going to equal vi squared, or initial velocity squared, divided by 2 times the acceleration. So I'm going to plug in my numbers, and my delta y is going to equal 310.2 meters. Well, I'm going to have to add that to my final velocity of my other problem, so I started off at 950 meters. I have an additional 310 meters, so I end up going 1,260.2 meters upward. So that is going to be the final height, or the final delta y, that this rocket achieves. Again, in segment 2, we're still going upwards, but we're slowing down. We want to know how much time does it take for the rocket to reach the maximum altitude. So from the previous slide, I know that my final distance upward is going to be 1,260.2 meters upward. I also know that from part B, my time is 24.37 seconds that it took to run out of fuel. So I'm going to figure out the time in this part of the problem. So I select an equation. Final velocity equals initial velocity plus a delta time. My final velocity goes to 0 in this segment, So it is the negative of my initial velocity divided by my acceleration, which is also a negative number, so those negatives do cancel, and I get a time of 7.96 seconds additional. So I add that on to my 24.37 seconds, and I end up with 32.33 seconds to get to the highest height that this rocket will achieve, 1,260.2 meters. So in segment 3, the rocket is now at the highest segment and it's going to start its descent. So my initial velocity is going to be 0. This is important. It starts at 0. My delta y is the change in height. It's going from 1,260 down to 0 at the ground. So my delta y is negative 1,260.2 meters. I want to find my final velocity. So I use final velocity squared equals initial velocity squared plus 2a delta y. Note that vi equals 0, so it drops out of the equation. The initial velocity is 0 because it's at rest at the highest point. That was my vf in the last problem, and it's my vi in this third segment of the problem. So final velocity squared equals 2a delta y. Final velocity equals the square root of 2 times negative 9.8 meters per second squared times negative 1,260.2 meters. It's negative because my displacement is going downward. So I end up with, when I take the square root, I have to choose positive or negative. And since my displacement is negative, my velocity is going to be negative. So I end up, and I know it's going downward, so I choose the negative 157.16 meters per second because it's going downward. And finally it asks how much time is it in the air. So I know the time from segments 1 and 2, 32.33 seconds. I now choose a slightly different equation. Final velocity equals the initial velocity plus a delta t. Final velocity divided by acceleration equals my delta time. So my delta time for this segment, and both of those negative signs cancel, is going to be 16.04 seconds. So I add that on, 16.04 seconds plus the 32.33 seconds it's already been in the air, and my rocket has been in the air for 48.37 seconds. And that concludes all the parts of this problem. So to recap, what's important in this problem is that we think about what we're doing, we apply our velocities, and one segment, our final velocity, may become the initial velocity of the next segment. We realize that there is acceleration going on at all segments of the problem. The first part of the problem, it's getting faster, faster, faster. Then the second problem, it's slowing down, so it's negative velocity. And the third part of the problem, it's getting faster, 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 but in the negative direction, so it is negative acceleration again. We're going to apply what we've learned in class. We're going to apply the 3 equations, but we're going to realize that the motion of this rocket changes, and we have to decide where those segments are, draw our motion maps, and then choose our equations and apply them correctly. You can watch this video as many times as it would be beneficial. I encourage you to do that, and hopefully this will help you make sense of doing your homework set. Thank you for tuning in.